All right, in this lesson, what we're talking about is how to find limits at corners, holes, jump discontinuities, and vertical asymptotes. And so typically what's going to happen whenever you're asked to do something like this, you're going to be given a graph, and you're going to see if the limit exists based on the graph of the function that you're looking at. So you can also find limits at corners, holes, jump discontinuities, and vertical asymptotes algebraically, but we'll start covering that more as we go on. So just a quick recap of limits so far. What we've been able to establish is that you can find the limit of a function. So as x gets really close to something, you can see what the y values are approaching by direct evaluation. Direct evaluation is simply whenever you plug the x value into the y value and you get something out. So what we might have here in this function is we've got a function, and it looks like as x is getting really close to 4, the y values are getting really close to 5. So if I wanted to use direct evaluation based off of this graph, I would just say that the limit as x approaches 4 for my function f of x is equal to 5. So I look at the x value, see what the y values are getting really close to. So they're getting really close to this value here, 5. And that's really it for direct evaluation. So we can take that principle and we can start looking at limits at interesting points on a graph like a corner. So in most cases, if you see a graph with a corner on it, it's probably going to be a piecewise function, or maybe it's some sort of weird radical function. So we've got, in this case, just some random piecewise function f of x. And so we're looking to see as x gets really close to 2, so we're going to find the limit as x goes to 2 for my function f of x, where are my y values headed? So in this case, my y values are getting really close to this peak right here, and that peak is located at y equals 3. So I would say that as my x values get really close to 2, my y values are converging toward 3. And so limits are going to exist at corners like this. Limits will always exist for continuous functions, or a function that's continuous at that particular point. And we'll be able to define what continuity means a little bit later on. So this is limits at corners. You're simply taking the x value, seeing what the y values are approaching. We might also be given something like limit at a hole. And so in this case, I've got a hole in the graph. And a hole is a type of removable discontinuity. And a removable discontinuity is typically found in a quotient function where there's a factor in the top that's going to cancel with a factor in the bottom. So something in your numerator cancels with something in your denominator, leaving you with a hole in your graph. Limits, in fact, are going to actually exist at holes. So if in this case, if I wanted to find the limit as x approaches 3 for this function f of x, I'm going to take my y values, and so as I get really close to 3 here, my y values get really close to the hole. And remember, with limits, you're looking near the value, not necessarily at the value. So in this case, my function's clearly not continuous at x equals 3, but as I approach 3 from both sides, my y values are converging to 4. So in this case, I could say the limit as x approaches 3 for f of x is going to equal 4. So limits are always going to exist at removable discontinuities, which show up on function graphs as holes. The next case is something called a jump discontinuity, and a jump discontinuity is one type of non-removable. And a non-removable discontinuity, in the case of a jump, means more than likely you're looking at a piecewise function. So if you have a finite jump in your graph, so you can see that this graph jumps from y equals 1 to y equals 4 at the x value. So if I look at my function, and as I go closer and closer and closer to x equals 3, my y values are getting closer to 4 from the left-hand side and 1 from the right-hand side. And since they're not converging to the same spot, I'm going to say that the limit as x approaches 3 for my function f of x does not exist. And you can write that as d in e. So in this case, my limit doesn't exist because my y values are approaching two distinctly different values. The last little bit here is whenever you have a vertical asymptote. And same with the jump discontinuity, a vertical asymptote is a non-removable discontinuity. So it's non-removable discontinuity. So whenever we have a non-removable discontinuity, our limit is not going to exist at that point. And you can clearly see if we tried to find the limit as x goes to 3 for f of x, my y values from the left-hand side are going up toward positive infinity, and from the left-hand side, they're going to positive infinity, and to the right-hand side, they're going to negative infinity. Since they're approaching two distinctly different values, I'm also going to say here my limit does not exist. So this is the basics of how to evaluate limits graphically by using a form of direct evaluation, and you're able to see, okay, if a function has a removable discontinuity or a corner, or if the function's continuous, my limit exists. If I have a non-removable discontinuity, like a vertical asymptote or a jump discontinuity, then my function's limit will not exist.